Hi there, Mr. Sutton here, bringing you this lesson on integration by partial fractions. In this one, we are going to be integrating using partial fraction decomposition. For your warm-up on this one, see if you can take the antiderivative of the following. All right, let's see how that went. So going from left to right here, we have basically a 1 over x kind of situation. So antiderivative is going to involve using ln of absolute value. For this first one, we have 3 ln absolute value of x plus 7. And then for this next one, we'll have 8 ln absolute value of 4 minus 3x. But wait, there's an inner function in this denominator. There was over here, but the derivative of this stuff was just 1. Here, though, we have an inner tail, a linear function with a derivative of negative 3. So this is actually going to end up being 8 over negative 3 ln of 4 minus 3x. So careful with those inner tails there. And then don't forget your plus c. Now that we've had that warm-up on using ln for antiderivatives, let's go ahead and use the method of partial fraction decomposition. So when do we use this method? That's the first big question. The situation we're going to be dealing with is this kind of situation here, where we have a bottom-heavy fraction, so a denominator with a higher degree than the numerator, and the denominator can be factored into unique linear factors. So it's important that these factors be unique. Like, we don't want 2x plus 1s or something like that, because then we're going to need to use a slightly different method. So this method requires bottom-heavy, unique factors. First step on this is going to be actually factoring that denominator. So we need two numbers that multiply to negative 18 and add up to 7. That would be positive 9 and negative 2. Next, we are going to set up an equation where we split this fraction up. So I'm going to write 4 over x minus 2, x plus 9 equals, now I'm going to assume that I can split this up into two fractions, one with each of the denominators in the original. So I don't know what the numerators are going to be, so I'll let the numerator of the first one be a. We'll say we have a over x minus 2. And then the other fraction I'm going to assume is going to be some b value over x plus 9. And the idea is if I pick the right a and b, there is some a and b that if I put them in there, I can add these fractions together and get what I started with. Now, our goal in doing this, the whole reason we want to accomplish this, is if we have different linear factors here, different fractions, then we can anti-differentiate these using ln. So if we can figure out a and b, and then we'll almost be done with this problem. So how do we figure out a and b? So first thing I'm going to do is get rid of all the fractions. I'm going to do that by multiplying by my LCD. Since this is an equation, I can multiply by anything I want as long as I do it to both sides. So I'm going to just multiply by x minus 2 and x plus 9. That's my LCD for this. And that'll give me 4 on the left side because the entire denominator is going to cancel out. On the right side, for this first fraction, the x minus 2's cancel, leaving me with a times the remaining factor of x plus 9. And then, for the next fraction, the x plus 9's cancel, leaving me with b times x minus 2. All right, we're getting there. So at this point, we're going to do something kind of sneaky, and that is I'm going to plug in convenient values of x to find a and b. Now, by convenient, I mean values of x that are going to zero out each of these different terms here. So one value of x that I might find very convenient is if x equals 2. If x equals 2, then I can write 4 equals a times 2 plus 9, and then this will be 0 over here, so I don't have to worry about this b value anymore. Okay, let's go ahead and solve this now for a. So this is just 11a equals 4, so a equals 4 over 11. Okay, that's great. Let's go ahead now and do the same thing for b. To figure out b, I have to get rid of this a term here, so I'm going to pick an x value of negative 9. If x equals negative 9, then I can write 4 equals, well, the a value is gone now because this factor is 0, so just b times negative 9 minus 2. This is really negative 11b, so we have b equals negative 4/11. So I found my a value and my b value. Now I am going to rewrite the original integrand to be this split up fraction kind of term with the a and the b plugged in, and I'll integrate from there. So I now have the integral of 4/11, that's the a value, over x minus 2, plus negative 4/11 over x plus 9, which I'll write as just minus 4 over 11. And I'm not going to worry about simplifying these fractions at this point. It'll actually be easier, you'll see on the next step, if I leave these little fractions in the numerators. So now going through and integrating, we can use ln for both of these cases. I'm going to have 4/11 times ln, or absolute value, ln of absolute value of x minus 2, and then I'll have minus 4/11 ln absolute value of x plus 9. And of course, don't forget your plus c. This is one possible answer. Just for the sake of argument, though, let's say that we needed to simplify this a little bit to match one of the answer choices in a problem. So I can factor out this 4/11, and then I just have these two ln's being subtracted. When I'm subtracting logs, remember that I'm dividing the things inside. So I can rewrite this whole thing as 4 over 11 ln absolute value of x minus 2 over x plus 9 plus c. So, as you can see from the last problem, the bad news is this process of decomposition has a lot of steps in it. The good news is it's pretty much always the same steps, just with different numbers. So pause the video, see if you need it for this one, and if you do, go ahead and try it out. All right, let's see how we did on this one. So do we need partial fraction decomposition here? Well, we do have a bottom-heavy fraction, and this can, if you try factoring it, it can be factored into unique factors. Sometimes you don't really know if it can be factored into unique factors until you factor it. So when in doubt, factor it out. What does this factor into? Well, I could use the AC method on this, but honestly, guess and check works just as well. To get 2x squared, I need a 2x and an x. To get positive 1 and a negative in the middle, that means I have to have two negative ones. So 2x minus 1 and x minus 1 is what this factors into. These are unique factors, so I can actually use partial fraction decomposition on this. All right, so let's set up our equation. We're going to set this integrand equal to, and now we need an a and a b with each of these denominator factors. So we'll have a over 2x minus 1 plus b over x minus 1. Now we need to solve for a and b. First step to that, again, was multiplying by our LCD. That's pretty much just whatever this integrand denominator got factored into. So multiplying everything by 2x minus 1 and x minus 1, I'm going to end up with just 5x minus 7 on the left side. On the right side, I'll have a times x minus 1, because these 2x minus 1s are going to cancel. And I'll have b times 2x minus 1, because the x minus 1s are going to cancel. Now I need to pick convenient values of x to get rid of a and b individually so I can solve for the other missing constant. I'll start by getting rid of b, although it doesn't really matter which one you tackle first. So what convenient value of x could I plug in to zero out this b term? How about 1/2? Basically, you're just setting this little factor equal to 0 and solving. So add 1, divide by 2. 1/2 is going to zero this out. So if x equals 1/2, then we have 5 times 1/2 minus 7. We do have something to plug in over here now. And then a times 1/2 minus 1. But the good news is this b term is gone. Let's go ahead and simplify each side now before we try solving for a. So over here, I've got 5/2 minus, well, this will be 14/2. So that's going to be negative 9/2. And over here, I've got negative 1/2 a. If I divide each side by a negative 1/2, or just multiply both sides by negative 2, that would be easier. I'm just going to end up with a equaling 9. Okay, well, that's actually kind of a nice result for all those fractions. Let's move on now and try to find the b value. So for b, I have to plug in an x value of 1 to zero out this a term. So I'll have, if x equals 1, then we have 5 times 1 minus 7 equaling, the a is gone, so just b times 2 times 1 minus 1. And this one's a little easier to solve. This is just negative 2 on the left side, and on the right side, 2 times 1 minus 1 is just 1. So we just end up then with b equals negative 2. All right, let's plug those back in now. I'm going to split up my fraction. I'm going to have, let's see, we had 9 over 2x minus 1 plus, well, actually, we're going to have minus, because it's a minus 2, minus 2 over x minus 1. And then I'm going to do my antiderivative here. Now, be careful. I'm going to have 9 ln of absolute value of 2x minus 1 divided by the inner tail of 2. So this is really 9/2 ln of absolute value of 2x minus 1. And then we'll have minus 2 ln of absolute value of x minus 1 plus c. So that's it. We are completely done with partial fractions. Till next time, this is Mr. Sutton signing off.